Hi everybody and welcome to our 1.4 video. Your goal after watching the video today will be able to understand independent events, mutually exclusive events, and do some of the associated calculations with that. So with that being said, we're going to go through a few definitions and a few formulas. I would say take careful note of the formulas because we're going to be using them for the next week or two here. So definitely something that you're going to want to keep track of. And if you have it and you take good notes, then it shouldn't be any issue when we go through and solve some of these questions. So first, starting off, back to basics, definition of probability. So this is just the measure of how likely an event will occur. Probability is always a value between 0 and 1. So you can think of 0 and 1 as 0% and 100%. So somewhere in that interval, you can't have negative and you can't have more than 100%. Basically, if something is 100% chance of happening, there is no possibility that it won't happen. So that means it certainly, without exception, will happen if it has a 100% chance. So probability for our formula for this is just going to be part over whole. So it's basically the number of outcomes that we're looking for divided by everything. So everything in this case, like we talked about in our last lesson, would be our entire sample space. So everything we have, we're putting our favorable outcomes on top. So a few examples that we'll see here. What is the probability of rolling a 4 on a 6-sided die? So outcomes on a 6-sided die are 1 through 6. So there are 6 total. And if we're looking for a 4 specifically, we'll find that right there. So there is only one outcome that has a 4 on it. So we have our outcome, which is one option out of 6 total, so 1 out of 6. The second one is pretty similar here. So we're going to put our favorable outcomes over our whole, our part over whole. So probability of the spinner landing on red, we'll do that one first. So red here. So we count this up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. So 12 total. And of those 12, how many are red? So you have 1, 2, 3, 4, 5 sections are red. Next, I'm going to have you do the calculation for green. So what is the probability that this spinner will land on green? So I'll have you put that in now, and I'll pause the Canvas video. All right, so taking a look at green, still 12 total. The difference now is we are not looking at reds anymore. We are just looking for where is this green. So we have 1, 2, 3. So 3 out of 12. If you simplify that fraction, 1 out of 4, if you put it as a decimal, 0.25, put it as a percent, 25%, all of those mean the same thing. 3 out of every 12 times you spin this, you should find a green underneath your spinner. Okay, so that's basic probability. From here, it gets a little bit more complicated. We talk about independent, dependent, mutually exclusive, a whole bunch of other things. So independent probability is the idea that two events are independent if the probability of the next event is not affected by the first event. So basically all this is saying is it doesn't matter what place you are in line. The person in front of you and the person behind you does not change what you get. For example, let's say I'm going to Crumbl Cookie and I'm trying to order my cookies. If the person in front of me ordering doesn't change the cookie that I get, I'm happy. But maybe the person in front of me gets that last brownie batter cookie. Well, in that case, I'm not able to get that cookie. The fact that they ordered it before me means I don't get it. So me getting that brownie batter cookie depends on the person in front of me. So if we talk about independent probability, we'd be talking about Crumbls that have unlimited supplies of cookies and they never run out. The person in front of you will never change what you're able to order. So if we look at something like example 3, are the events rolling a 6 and then rolling a 2 on your second roll on a 6-sided die independent? So what this is saying is, does the fact that you get a 6 the first time through, does that in any way, shape, or form change whether or not you get a 2 the second time? Well, if you roll a die like a normal person, it doesn't. We're not slicing a face off of the die or cracking it in half or anything. All 6 sides remain exactly the same for each roll. So the idea for this is we still have an outcome out of 6. Doing a roll does not change the fact that we have 6 sides of a die. So as long as you don't, stomp on the die and split it into a million pieces, the first roll is not going to change the outcome of your second roll. We'll get into this exact calculation soon, and how we actually would calculate the probability of rolling a 6 and then rolling a 2 right after. But for now, we're just determining, does this change our sample space? The answer is no. So because of that, it is independent. So independent because the second roll probability is not changed by the first roll. So an explanation like that would be sufficient to prove in words that an event is independent. The second type of example you'll see here for independent events in terms of determining whether or not they are independent is something where you're drawing something. So marbles out of a bag, lottery ticket, something like that. So in example number 4, we have a bag of 20 marbles and it has 4 blue, 9 orange, 1 red, and 6 green. So 4 blue, 9 orange, 1 red, and 6 green. So altogether that adds up to a total of 20. So you draw 2 marbles out of the bag, one at a time. So you take one, then you immediately take a second one. Are the events of drawing an orange and then drawing a red marble independent? Why or why not? So let's start off with the probability of drawing an orange. Well, we have 20 marbles, and let's say that I go ahead and I scoop this one up. So that's 1 out of those 20, but I could have scooped up any of the 9 there. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 successful outcomes that I could possibly have scooped up. Any of those 9 would be orange. I'd be happy with any of them. So if I do that and I take that orange marble, well, that orange marble is now out of the bag. So the issue now, if I'm looking at my red marble, is that in my bag of marbles that I've already taken an orange marble out of, my sample size is no longer 20. My sample space goes down to 19. So because I've taken one out of the bag, I've changed the whole. And because I've changed the whole, I've changed the probability of drawing a red marble. So there's still only one outcome that's red, 1 out of 19, but that probability is actually more likely now because there's less orange marbles that I could mistakenly pick up. So in this case, we see that we have a dependent event because drawing orange changed the probability that we draw a red marble. So this can be a little bit tricky, but basically a good rule of thumb is that if you take something out and you don't put it back, you are changing the probability of whatever happens next. So in that case, you are looking 9 times out of 10 at a dependent event. All right, so we have some formulas for this that help us out. So if we define our first event as A and we define our second event as B, this is shorthand that helps us write this a little bit quicker. The probability of A happening we write as P parentheses A. So P in this case is not a variable. We're not solving for P. P parentheses A is just math shorthand for saying the probability of A happening. So it's like a sentence. So we're not doing any operations to P parentheses A. We leave it alone. The same thing, probability of B happening, we just do P parentheses B. Again, this is math shorthand. You will never be touching the P parentheses B. We're not going to be doing any operations or manipulation with that. So you'll always just leave that where it is. So the formula that we're looking at is the probability of A and B. So getting 2 events at the same time. For independent events is we just multiply the probability of A times the probability of B. So if we go back to our example of rolling a die, the probability of A, which is rolling a 6, well, we have 6 sides of a die. Only one of those 6 sides is a 6, so that's 1 out of 6. The probability of B of rolling a 2, again, 6 sides of a die. Only one of those sides is a 2, so it's 1 out of 6. They're independent. The first one doesn't affect the probability of the second one. So if we're going to do our probability of A and B using our formula, we would have probability of A times the probability of B. So I'm going to pause the video now, have you plug those in and see what is the answer for the probability of A and B. All right, so hopefully you got that answer in, and we are just going to move forward with evaluating. So probability of A times probability of B. So when we multiply fractions, we go straight across, so top times top, bottom times bottom. So 1 times 1 is 1. 6 times 6 on the bottom is 36. So the probability of getting a 6 and then immediately rolling a 2 right after, that'll happen 1 out of every 36 times that you try. So that's our probability, 1 over 36. So similar here, we're going to take a look back at our marble question from above. So this time we're going to replace the marble after we draw it. So if we draw 2 marbles, we'll take one out and we'll put it right back in. So by putting it right back in, we don't change our sample space. It resets the bag to the original probability, so the probability is unchanged. So by replacing it, we guarantee that we have an independent bag. So A is drawing the orange marble, and B is drawing the red marble. So let's refresh these probabilities. So go ahead, tell me what is the probability of A drawing an orange marble? And what is the probability of B drawing a red marble? All right, so if we revisit it here, orange marble, we had 9 out of 20, 9 oranges out of 20 total. And then red, this time because we replace it, it is over 20 again. So it's 1 over 20 now. It's not 1 over 19 anymore because we don't get rid of anything. We put everything back, so it always resets to 20. So now finding this probability, we'll do probability of A and B. So 9 over 20, and then multiply it by 1 over 20. So on top, 9 times 1 is 9. On the bottom, 20 times 20 is 400. So you can convert it to a decimal. You can leave it as that fraction. Any way, shape, or form is totally fine, whatever you are comfortable with. But that is our overall probability here. Okay, so those are some examples of probability calculations. A lot of what you're going to see on our worksheet here, we're going to be using this formula. So definitely want to have written down and keep track of there. The last vocabulary that we're going to take a look at is mutually exclusive. So mutually exclusive, if we have 2 events that are mutually exclusive, this happens if the probability of both events happening at exactly the same time, so instantaneously at the same time, is impossible. They cannot happen at the same time. So something is mutually exclusive if it can't happen at the same time. You got a probability of 0. So again, if we denote probability of A and probability of B, our formula for mutually exclusive probabilities is we can do the probability of A or B happening, so not and, but A or, so either one, probability of A plus the probability of B. So let's talk about some of these examples. Let's start off with number 8. A spinner has an equal chance of landing on each of its 8 regions. After spinning it, it lands in region 3, or it lands in region 6. So we first have to determine, is landing in 3 or 6, so landing in 3 or landing in 6, are these mutually exclusive? Another way of saying this is, can we be on 3 and 6 at the same time? The answer to this, if you've ever spun a spinner before, is that there's only one arrow on a spinner. It can't touch 2 things at once. So you're either on 3 or you're on 6. If you're in that in-between region, you're not on either of them. You're just in the middle. So this is mutually exclusive. So this is mutually exclusive because it can't be on both. So what this allows us to do for calculating this formula, if it's on a 3 or a 6, so basically what this is saying is, if you spin a spinner and you're betting money that it's a 3, or you're betting money it's a 6, basically you're a winner if it lands on 3, and you're a winner if it lands on 6. We want to find the probability total that you win. So the probability that it lands on a 3 or that it lands on a 6, because those are the outcomes that get you paid. So if we have 8 regions on our spinner, the probability that it lands on, a 3 would be 1 out of 8 of those regions. The probability that lands on a 6, 1 out of 8 of those regions. So because this is mutually exclusive, the probability of 3 or 6, we can use our formula from above, we just add them. So 1 over 8 plus 1 over 8. So not multiplying here, adding. Be careful adding fractions. Remember, the bottoms have to have common denominators. The bottom numbers have to be the same. When we add fractions, we do not change our denominator. We keep it the same, and we add the top. So 1 plus 1 is equal to 2. So 2 over 8, 1 over 4, 25% chance. Any of those is totally fine, but this is our answer here. The probability of you winning money, if it lands on a 3 or a 6, is 2 out of 8. All right, so example number 7 gets a little bit more nuanced, a little bit more tricky here, and it's our last one for today. So a box of chocolates contains 6 milk chocolates and 4 dark chocolates. 2 of the milk chocolates and 3 of the dark chocolates have peanuts inside. So what you're seeing, if you've ever eaten a chocolate bar before, is sometimes they have variety. It's not just chocolate, they have other things inside of them. So if you're thinking about mutually exclusive already, and you're thinking about, okay, I could have a chocolate bar that is just milk chocolate or just a peanut bar, well, sometimes you can mix the two things together. So if the two things are happening at the same time, we know that they are not mutually exclusive. So if you are looking to randomly select and eat a chocolate, we are looking for the probability that it is milk chocolate or it has no peanuts inside. So that is kind of the idea for the questions that we're working through is it possible for two things to happen at once? And looking at specifically what they're asking you for. So again, we have 6 milk. We have 4 dark. 2 of the milk chocolates have peanuts. And 3 of the dark chocolates have peanuts. And we are trying to see if we can get something that is probability of milk or the probability that it has no peanuts. Well, unfortunately, these two things, milk and not having peanuts, can happen together. Because we have peanuts mixed into our milk chocolate and because we have milk chocolate without peanuts, 2 of these things happening at the same time is possible. So because of this, these are not mutually exclusive, can both happen at the same time. So with the information that we have right now with our formulas, we're not going to solve this one because they are not mutually exclusive. So that's the conclusion of the video for today. Thanks for following along. You'll have some good questions to test your knowledge of these coming up here shortly. As always, if you got questions, let me know, but go ahead and get started.